Hey, good evening, everyone. First thing is, there's a typo on those solutions. Typo. The answer, the number 23, from the chain rule practice. Any parentheses that has a 4x should say parentheses 5x. Any parentheses where you see 4x, you replace it with 5x. There's two places, do you see it? That's the chain rule practice, the solutions. Any four, just make it a 5. Typos. They're 5.
Okay, why does 5 turn into a 4?
Now, we'll work that problem. Okay? But before we do 23, let's do 21 from the chain rule practice. So this chain rule practice. Okay, practice on chain rule. Okay. Practice on chain rule. Number 21. F of x equals x times the square root of 2x plus 1. What's the overriding rule I should use?
2x minus 1, I think.
Oh, you're the best, is it?
Mm-hmm.
Thanks a lot. 2x minus 1.
You can use.
Rule. Product rule. We got to start with product rule. In front of square root 2x minus 1, we have x. Now, if it was just a 5, we would not need product rule because it's a constant. If there's an x in front of square root 2x minus 1, we got to think of this as product rule. So, here your m, your n, f prime, m times n prime, plus n times n prime. I think 3 of these are a piece of cake. What's m?
X.
What's n?
2x minus 1, 2 power half.
What's n prime?
1.
I'll even write it, just so you know there's something there, 1. 3 out of 4, we're like, ba 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 done. And then you're like, whoa. And if you have to, go off to the side to say, listen, if n is equal to the square root of 2x minus 1, which is 2x minus 1 to the 1/2 power, what's that derivative? Right? The half comes in front. This is chain rule, and then we decrease this by 1, and I substitute g back in there. There's g.
2x. 2.
A lot of students think that's the derivative, but you won't. It's like 1/2 in front, decrease this by 1, now multiply the chain. What is, there's g. What's the derivative? What's g prime there? What's the derivative? 2x minus 1. Times 2. And when there's that g prime chain we're always talking about. Now, you can cancel
2
before I shove it up in there.
2.5.
Now, this 2's come out. And everyone, isn't that 1 over a radical 2x minus 1? So I'm going to write it nice and clean. Here it is. That 2 cancel with that 2. There you go. So now I'm going to put it back in here. Square root 2x minus 1. Yeah, I'm done. But everyone, it's good to write an answer with a solo fraction. So from here on out, it's just algebra. Common denominators and things like that. So let me write this again. X over square root 2x minus 1 plus square root 2x. I'm done. Now I'm going to write this one fraction. Common denominators. Well, that has a square root of 2x minus 1 in it, right? This is over a what?
1.
1. So how can I make these common? Just go over this guy and multiply what? Since this is over 1, just multiply a square root of 2x minus 1 over a square root of 2x minus 1. And you now have common denominators. Yeah, I put the parentheses, but I thought I would. So that's 1. And you'll notice this looks really neat now. Yeah, and when the common denominator is this. But look what you got in the numerator now. You've got x plus, and what's 2 squared of 2x minus 1 is multiplied by each other?
2x minus 1.
Do you see how you can leave this answer? You got like terms in it. Like terms, 3x minus 1 over. Ta-da! Lot neater than that other expression. Good job. Let's do 23. Oh, we're just noting that the solutions to number 23, there was a typo. If you see any parentheses that had a 4x, 5x, or it now, so you can see the actual answer. So you got sine, is that cubed? Sine cubed x. Tangent 5. Hey, do you all agree let's do product rule?
Mm-hmm.
So I'll leave this up here. M times m prime plus n times m prime. Your m, your n. This time I think 2 are real easy. Look at it right here.
Sine cube x
Sine cube x. Everyone, if you didn't know this, when we write sine cubed x like this, that means sine of x all in a parentheses cubed. That means 3 sine x's. Sine x times sine x times sine x. Just to make that note, it's just an easier way to write it. This n over here is tangent 5x. But I think we should go off to the side and figure out these other derivatives. So m equaled sine cubed x. Can I think of it like that? Right? Let's find m product. All right, Kel, it looks like a chain rule. 3 comes in front. It's like a chain rule. Decrease all this by 1. Put your g back in. G was? Now multiply g prime. What's the derivative of just the sine of x? Got it. There it is. That's it. That's m prime. Is that okay with that? That's chain rule. 3 sine x to the second, multiply derivative of sine x, which is cosine x. So that all goes on m prime over here. All right, so I'll put a big parentheses and just go 3 sine, you know that's an easy way to write that, cosine x. Okay, we took care of all that. Let's take care of that m. Oh, this is going to be a lot easier. But it is chain rule. And when by chain rule, we know the derivative of tangent of x is secant squared of x. So this will be secant squared of 5x times your g prime. Did everyone hear that? G prime is 5, and I like to put it in front like you do. Problem done? 5 tangent squared 5x. And now you'll note those typos that I had 4 x's in there on the original document. The 5 x's. That's it. But is there anything nice we can do? It's always good to get those coefficients way out in front. See this 5?
I think you made a mistake.
Oh, it's secant squared. Thank you so much. It's all right. You're the best. He's like, hey, the derivative of tangent is secant squared. Thanks again. And the final answer, and I'm just going to put the 5 out in front of all that stuff. 5 times sine cubed x times secant squared of 5x. There's the plus, then there's a 3. 3, and you could do what?
sine squared x, there's a tangent 5x, and there's this cosine x. Well, it really doesn't matter the order. I'll do that, then I'll do that, then I'll do that. That was done fine. I guess there's one thing we could factor out of it if you wanted to. What could you factor out? Sine squared? Sine squared of x? Good. So if you want to factor out, that's why on the solution document I wrote it 2 different ways. If the student preferred to factor out that sine squared of x. Okay with all that? Oh, awesome. You'll know, we just get more and more practice with chain rule. More and more practice with chain rule. Hey, a couple more. Because I know you wanted to do a couple textbook problems. We'll do those.
I have one more question. How do you know secant squared?
Oh, it's just, you want to, we can prove it. But you knew sine's derivative's cosine, right?
Yeah.
But it came from, like, oh, maybe we should memorize these. It helps. But if you wanted to see it mathematically proven, you could call tangents sine over cosine and do like quotient rule. And you'd come out with that.
Okay.
But that's what it is. Secant squared of x. That's the derivative of that one. Well, man, anybody remember the derivative of secant?
Secant x tan x.
Secant x, tan x. Secant x, tan x. And so I know that they don't come up as often as the sine and the cosine, but we do, there's derivative of tangent of x or secant of x every once in a while. All right. Now, textbook, number 31. How about this guy? I want to try to get this derivative. Sine of tan of 2. Okay, let's start it. That problem would be
Cosine
cosine of,
tan of 2x.
I'll put my g in, and then I'll do g prime. I'm going to put your g back in. Stick it back in there. Tan of 2x. But chain rule means I need to get the derivative of that. Multiply. Which involves another chain rule. What's the derivative of tangent of 2x?
So
Secant squared of 2x times a what?
2.
By chain rule, times a 2. Just like before, I want to look at that one. Did anyone see that? If you get that one, you get chain rule. Because it's like a double chain in there, isn't it? If you get that problem, you're like, all right, sine of blah. Okay, cosine of, put my g back in, times g prime. But you're like, but how do I get that type of derivative? Well, that involves chain rule. Find the derivative of tangent 2x, it's similar to this. And we get that. So final answer, I'll just put the 2 in front. 2 cosine tan of 2x. Multiply by secant squared of 2x. Awesome.
Didn't we miss an extra 2?
Did we? Where would you think?
Well, if you take the derivative of... Oh, no, never mind.
Good call. See, you saw it. It's neat because it's like, here's that f of g, right? And you're like, you're g. And so we did sine, cosine, put g back in. And then we just had to multiply this g prime, which is like that derivative which involves chain rule. Good deal. And then the other one, Cal, is 33, which is something, I'll be honest, I haven't really covered it. So blame it on me.
Yeah,
Yeah. So I'll put it down over here. When I haven't done something like this, these are not often, they don't come up often. They come up very rarely. Cal, you have this problem, you can tell me. I can check back with you after you finish Comp 3, or maybe Diffie Q. You know, DE, differential equation, I can check with her to see how many times something like this came up. Probably not too often. What exponential function do we see all the time? E to the x. And what's that derivative?
E to the power x.
That's the exponential function we see all the time. All the time. See e to the x, e to the x. Sometimes see e to 2x, e to 3x, e to 4x squared, all, etc. And out of nowhere, when they come up with something, maybe like, I'm just going to put this down as an example before we do that one, Kelly. 2 to the x. Ooh, e is 2.718281828184590. It's an irrational number. 2 to the x. To find this derivative, it's like e to the x. Will you just write it again? But you also have to put the constant natural log of 2 and multiply to it. Don't get too concerned with these. Not like you see these every day, do you? You don't see 2 to the x's and 3 to the x's and 4 to the x's. But how would you differentiate them? That's how you do it. So you see this? It's like, the whole idea is this, Kelly, I have to say, I rewrite that exponential function and I multiply the natural log of that base value. Whatever the base is. If that was a 3 to the, I'll put ln of 3. That's a constant, by the way. It's an irrational number. Cool. So, what's the most complicated case for these rare cases is where you have any base, right, raised to some exponent different from e to the x, right? Well then, the derivative will be this. Make sure you write the natural log of that base. Do that. Rewrite the base to the exponent. Okay? Kind of like this. But if this exponent here, everyone, is something a little bit more complicated than x, like 2x squared or 5x or 3x, then we're going to have to apply chain rule and multiply the derivative of that exponent. Does that make sense? So if needed, derivative of whatever that exponent is. So before I do this, how about this guy? 2 to the 4x. I'm going to find that derivative. First of all, natural log of what number? 2. And when we rewrite this, 2 to the 4x. Now, before you leave that as your answer, tell you what's the derivative of 4x. See right there, that's the f prime of g. And now all we have to do, that's your little g there. Well, what's the derivative of 4x? Just up. Did anyone say? It's ln of 2 times 2 to the 4x times a 4. If you want to put the 4l and 2 in front, you can. What would that? You may know a way to simplify that if you wanted to. 4 natural log. Can I move that up here? Yeah, you can write that as natural log 16 if you want. 2 to the 4th. Put 4l and 2 is fine. I'd leave it like that. Oh, keep in mind, Cody, we got a lot of these. No, I seriously want to know at the end of this course, or the end of Calc 2, how many of these you see? They rarely come up. Usually the exponential function is e to the x. By the way, it works in the same way. You should see that. It works the same way. Watch this. Get the derivative e to 4x. Okay? First of all, natural log of what's the base? E. Rewrite e to the 4x. Now, what's the derivative of 4x?
4.
That's the answer. Now, we've done a bunch of these already. Because what's the natural log of e, Kel?
1.
See? See one and this similar? But we do so many of these, ln of e is always 1. It's just this, oh, you gotta write natural log of 2. All the time. Tons and tons of these. Those are rare.
Well, you include this in the test. But doesn't the natural log of e cancel out?
That's right, because natural log of e is just a what?
1.
A 1. So what's the best way to write this answer?
E to the 4, oh, 4 to the e. 4
You said it.
to the
You
4x.
said it. I love it. 4 e to the
4x.
4x. And so what's e to a 5x become?
5.
5
e
e to
the
5. See, those are what you're gonna see all the
So
time.
then that wouldn't be there, is that right?
That's right.
Okay.
Now let's do Kel that actual problem for the book. Let's do it. She goes, now I want to see this problem. It's from the textbook. It's from 3.4 is on page 205. Y equals 2 to the sine pi of x. First of all, natural log, what number?
2.
Check. Second, would you just rewrite that whole expression?
Yep.
2 to the?
Sine pi of x.
Now here comes the chain. There's your g. What's the derivative of sine of pi x? It's just like that one earlier, right? Sine of pi x. Yeah, that's your g. What's g prime?
Cosine pi x.
Cosine of a pi x, chain, times up.
X.
On the grid? Oh, good. I'll just put it in here, right here. Here it is. Pi cosine pi x. No, Kel, I'm being honest with you, don't see many of those. I mean, it's great. Here's the new lesson on chain rule. So the author really wanted to throw everything at you. 2 to the x's and stuff, you know, and every trig function, cosine, sines. That'd be the answer.
Will I see one student say next Tuesday?
Probably not. You know why? Go through that book. See how many more you got of those. That's the idea. It's like if you had like 10 more to practice of these, oh yeah, put it on there. If this is something like, oh gosh, this comes up in Calc 2 and Calc 3 all the time. Or DE, I have these every day. Well, heck, I'm gonna have it on there, right? But seriously, the kinds of things I'm seeing all the time are these functions. And these functions. Which Amber, we've seen across, right? Yeah. The derivatives. 5 e to the 5x, right?
Yeah.
And 4 e to the 4x. Hey, before you get hooked on that, you see a lot of these too. Anybody know what rule you gotta use there?
Product.
Good, product, it wasn't a 4 in front, you need product rule there. First time for the second time for good. Just to recognize that, that's outstanding. Things like that, product rule, or this guy. Product rule. Right? 2x, cosine, product rule. Product rule, all of them.
What about if you're in like 400 level, like when you do advanced calc and all, it don't come?
Nope. But it's like once in a blue moon you get this 3, and you go, oh, how you go, oh yeah, natural log of the base, natural log of 2, or natural log of 3, rewrite, and then you do the derivative of it. Cool. All right, these are important. What about our SCSES? Differentiate that way, right? For sines and cosines, those come up a lot. But yesterday, we added some inverse trig functions. So can I put them down?
Yeah.
And if you don't mind, I'm going to write them in terms of u. What if y equals arc sine of u? Then I could say the derivative will be whatever u prime is over square root of 1 minus
U square.
q squared. How about inverse cosine? U.
Same thing but with a minus.
How
Negative.
about we write negative sine? Does that work?
Yep.
Negative sine. Just like arc sine. Same thing, but negative.
Can we do that on the test?
Yeah. If you already wrote the arc sine. Because that'd be the same as what? Right? You have to like draw an arrow. Ah. I'll be honest, through Calc 2 and Calc 3, this is the inverse trig function you will see the most, this guy.
Cotangent. No, so tan.
Inverse tangent. He doesn't have a radical. Oh, I want to write in terms of u, right? So the derivative will be 1 over 1 plus u squared times derivative. So here, just so you can follow that example, everyone, what's this derivative? Inverse tan of x, which is also written as arctan of x. What's that derivative if it was just an x?
1 over x squared.
So if x 1,
Well, 1 plus x squared, sorry.
I mean, that's one you go, I want to make sure I'm familiar with that. Arc sine too, yeah, arc so cosine. Those are the three I need you to know, Belraj. Right? Those three. But you can look at your textbook. Aren't there 3 other trig functions?
Yeah, cosecant, secant.
Might as well put them down, right? You're taking notes, everyone. You know it's in the book, but a lot of you refer back to your notes when you go into Calc 2, and you might want to find this. And you go, well, what page are they on? You'll see them on page 214. Okay? Cool? But I said, tell one of these.
No,
My
say,
test, right?
say in case if it was like cosecant inverse of u. So it will be like what? 1 over u prime? Like that?
Got it?
Okay.
I love it. Hey, watch this. Might as well add this to the list. Don't write it like this. What's this one? Same as that, but
Negative.
let me just draw an arrow. You want to see that? Oh, inverse cotangent. Same as inverse tangent, but just what? Now, which ones you don't see too often? But we need them in your notes because while they don't come up too often, every once in a while in a calc course, you get them. Calc 2 course too. And you'd want to know them. You want to impress your Calc 2 for that one. Who's missing? What 2 trig functions? Secant, cosecant. So I'm going to write inverse secant and inverse cosecant. So add them. Here they come. Do you see these often though? Well, this looks like this guy. Basically. Rather than writing 1 minus u squared, does everyone see what I wrote? But there's one other thing. In this denominator, right here, is another little u. And when you can see this, you'll see this written on page 214. And when that started with a C, that started with a C,
So negative.
and it was negative that. This started with a C, it was negative that. This inverse trig function starts with a C,
Negative
it's
sign.
negative something on the board. Which one is it?
Sine.
Negative of that. But these two you will not see what? Often. Which ones will you see a lot of? This one and this one. See a lot of those. I'd say inverse cosine too. But I still don't see them as often as those. So hey, again, since it comes up so often, what is that derivative?
1 over 1 plus x squared.
You go, why is that so important? Why is Professor Rushing saying that's so important?
That's the tangent line.
Yeah. And everyone, in about 3 weeks, we'll be doing something called antiderivatives. And the symbol, you go backwards. You go this way. And the symbol you use is the integral symbol. And out of the blue, you're going to get this problem in the book. And you're going to look at it and go, I remember doing one like this in class. And you'll be like, what technique am I going to use that looks confusing to you? And they're trying to see if you recognize, oh, antiderivative, this will just pull it right back to what?
Tan inverse x.
That right there. So you don't have to write that down. That's future topic. That's an integral symbol. That means you're gonna find the antiderivative expression. And since derivative of constants is always 0, we just put plus constant there too. Cool, so that's what I mean. That's why that one's pretty darn important. Hey, let's try one now, everyone, about where we need chain rule. So, good luck. Now you'll get it. Ellen, can you find the derivative of inverse sine of 9x?
Yep.
Could you find that?
Yep.
You're sitting there and you're like, oh, that's the one with the square root. It's not negative, it's positive, right?
So it should be 9 over 1 plus 9x squared.
And watch, I'm going to make an error. This is what I see on a test. Students, remember to put the derivative of this here. They remember the 1 minus. And they remember the square. Wah, wah. I see stuff like that.
Oh, 81, sorry.
Right? But no, not you, Art. You got it right. That was right. This is what I see. I see that. Or sometimes I see 1 minus x squared. What's wrong with this?
81.
This, yeah, you got it. It's this.
That's good.
No, you got to square that whole thing. Now, if you put the parentheses there, that's good. But I think you all know how to square a 9 and an x same time. What do you get?
81.
81x squared. Happy face. There you go. That's it, though. Leave it. Oh, no, you can't factor. I can factor that. It's a difference in square, but you can't factor anything out of it. You got a square root of 1 plus 9x and a square root of 1 minus 9x. That's it. Was that what we got that? Great job. Great job. Will you see these often? Not even this, even though I have it up here, it's just negative that. You just don't see it too often. Which ones do you see a lot of? Those 3, and I would say most of all, those 2. Go, Raj, if you have those inverse trig.
On 3.5, can you do number 80?
Yeah,
That took me a long time. I couldn't still figure it out.
you bet. So, in these sections of the textbook, pretty long, right? And sometimes I look at someone who's I look at every problem. I'm like, you know, don't want to get caught in something that's just going to be like, Sometimes I see a cool problem. Author makes a really good problem, but it requires something called problem solving. It's not your natural, typical two-step get the answer, right? It's not your typical just get the derivative. It's got a picture, it's got an image, and we got to look at it and we got to examine it. So we're going to problem solve together. Does that sound good? Don't worry when you problem solve, Art and everyone. You try a problem, and you don't know what to do. You don't know where to start. We'll start somewhere. We start brainstorming, we'll get this thing, okay? Let me just draw this. So this is from 3.5. Before we move out of all these inverse trig derivatives, everyone, here's the image. Whoop. Whoop. I see they have an ellipse in there, huh? And when there's an ellipse, I see over here, off to the right, they have the number 3. They got a pole that went up like this. And way over here, there's a -5. Don't worry, this isn't drawn to scale. There's a -5 right there. And the top of this post, they drew a tangent to that curve. And it's right there. So when that is tangent, I'll just put a big dot right there. When it's tangent to this curve right here, I'll just thicken that. I'll thicken that ellipse. So this point is the point of tangency, right? They didn't tell you what it was. They did give the equation of this ellipse here, though. Now, when you know how circles look? Circles look like this. Right? This is circles. When they're elliptical, you get equations like this. X squared, 4y squared equals 5. That's the equation of that ellipse right there. Okay, that was good. Now, what's the question?
How far above the x-axis is the lamp located? Here's the lamp. I guess we gotta find the height of the lamp, huh? But keep in mind, everyone, what problem number was this again?
80.
This is number 80, the dead last problem in this section. Did you ever see the textbooks that level A problem, level B problem, level C problem? Well, this is level what? Level C. But involves problem solving, we'll get it. We'll just play with this. We'll just play around with this. I see a straight line in here, right?
Uh-huh.
Everyone, do you know how to find the slope of this straight line?
Yeah.
Yeah, but to get slope of a straight line, rise over 1. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1.
Yeah.
Does that work? I don't know what this point is. Is everyone okay if I call it x comma 1?
Yeah.
All right. I don't know what you are, but I'll call you point x comma 1. True? So what would be the slope of that straight line?
Isn't it negative x one?
What would it be if I did slope from x, y, and what's this as an xy coordinate?
Negative 50.
But if I'm thinking about slope, let's start there. We're trying to get to what? The height of this lamp?
Uh-huh.
But do you agree somehow we can use calculus and we can look at slopes? So I'll start there. I know. Hey, you're point xy. I know you're going to be critical and help me solve this problem. So xy, the slope of the straight line would be y minus 0 all over x minus negative 5. And what does that equal?
So y minus 0 equals
Y minus 0 over x minus negative
5.
5. Can I simplify that?
Yeah.
What do we get?
Y over x plus 5.
Cool. Now I'd like to be able to set this equal to something. Do you agree slopes of tangent lines to curves is equal to the derivative? So that equals dy dx? Well, I got an equation here. So now we're going somewhere, right? Well, at least we got this thing going. We're like, oh yeah, that's like, this should be equal to the dy dx of that equation. Huh? So let's try that. Now, do you remember how to differentiate something that's this? We gotta do implicit differentiation. Let's do implicit differentiation. What's your thought? 0. What's your x squared?
2x.
Do you remember how to do this?
8y.
Differentiate that, and then you're gonna put down what? dy dx, right? Good. All right, let's see. 8y to the first times a
dy dx.
dy dx. Now, can you solve for dy dx? What would it be?
Negative 1/4 x over y.
Good job. You subtracted 2x on both sides. Does everyone see that? And then he's going to divide the 8y. So subtract 2x on both sides and divide the 8y, right? Josephine.
Where'd you get the 2 and the 8?
The 2 and the e. I'm sorry, where's it? Oh, right there?
Yeah.
That ain't right there. So what I'm doing right here, if I'm going from this step to this step, I am differentiating both sides. I didn't write my writing, but what I'm doing to this equation, this is equation out of ellipse, I'm doing this. I'm differentiating that side,
Is there,
and I'm differentiating this side with respect to the letter x.
is there wherever there's a y?
That's right. You got it, implicit differentiation. But Josephine, I didn't write that, but please feel free to do that. And I'll just rewrite the ellipse equation right here. The equation of this ellipse is x squared plus 4y squared equals what? 5? So what's dy dx equal? Negative 2x over,
8y.
and I heard you could reduce that. What would that be?
1/4 xy.
I like it. So can I put that over here?
Yeah.
Everyone agree?
Yep.
Now we're going somewhere. This is where I started. I'm like, I have no idea where to start. But I'm seeing a tangent line, and we're thinking calculus, slope of tangent line is derivative. And then I saw a straight line, and I said, well, I can just do rise over run on that, right? So let me substitute this right here. And let's see if we can get anywhere. And I wonder if you can notice what I did. I was thinking slope of line is equal to derivative of that equation. That's what I did, right?
Now, it would be great if we could solve that equation. We could figure this out. But if we can get that point, we can get that point over there. Right?
Mhm.
We definitely can get it. Boy, what is this? Now, any idea how I can play around with this math equation? What if I cross multiply? What do I get?
4y square equals to x square plus 5 negative x. Negative x square minus negative. Why don't you bring it up, bring it over here and to 0? Let's see.
And this would work. This could give us an idea what's going on here.
Where did you get the y, x plus 5?
The y over x plus 5? That came from slope of straight line. I just called this point what? X comma y? And I said y minus 0
Oh, y
over
squared minus y.
x minus negative 5.
Okay.
No calculus either, right? Joe? Hey, what's this point? Well, the x value is what?
3.
3. I can't call that y though, can I? You go, why not? Because it's not on the curve right there. But anyways, I'm looking at this equation. If I cross multiply, I get 4y squared equals negative x squared
Professor,
minus 5 times what? X. Do you all agree? I'm going to do that. Everyone okay if I cross multiply?
Yeah.
All right, here I go. This times this would give me what? 4y squared? What's this times this give you? 4y squared equals
Negative x squared minus 5x.
negative x times x plus 5, which is negative x squared, but is it exactly?
Minus 5x.
Is it exactly the equation? It's
No.
close to it, isn't it?
No, Professor, what, here's my suggestion.
Sure.
If you bring the, because we can like single out the y, and once we single out the y and we can substitute y for that value.
Yep. You could do that.
Yeah.
You can add the x squared to the other side and then take the negative of that 5 and that x and put it on the left side and then I give up after that.
Hey, everyone, you know what's neat? Right now you go, boy, we did a lot of work. A lot of you noticed that this equation kind of looked like what? The equation up there.
Yeah.
Kelly done it? But if you look closely, it's not exactly the same, is it?
Okay, pull out a negative.
But everyone, all we're trying to do, you and I are trying to figure out what is this daggone what?
That's
Problem.
amazing.
And we did some great things. We took the derivative, we set it equal to slope of that tangent line, so we have one thing less to do to figure this thing to solve this. It's one of those good problem solving skills. Can I substitute something for this?
Yeah.
Maybe I'll be able to solve this. I would love to have this equation all in terms of x. Well, since this point of x comma y is on this ellipse, what is 4y squared equal to in that equation? What would 4y squared, if you could isolate that, what is 4y squared equal to in that equation?
5 minus x squared, yep.
Can I substitute that there?
Yeah.
Then we're going to solve for x, and that'll be our crux move. We'll have this problem solved. Because we'll get that point on that curve. Do you all see that? So it's fine. You go, it's a problem solving skill. You go, I've tried everything. I did a little calculus, but can I substitute something? And you look back at your work and you're like, ooh, I could substitute something for this 4y squared. What can I put in place of this? See this equation right here? Let me just go up here and go what? 4y squared is equal to a what? 5 minus x squared. All right, I'll take this. Remember, I'm going to put it in place of this. Right? Can I substitute that for that? Because that's from that equation. See that? X squared plus 4y squared equals 5? So 4y squared isolated, well, I just subtract that x squared. I'm not saying. I could put it over here. And don't ever think of this problem as, whoa, this is nasty. It's more fun. We're just trying to solve it. It's math problem solving. And see if you can solve this equation. I know you can. Anything cancel on both sides?
X squared.
And you gotta laugh. You're like, oh my gosh, this is gonna be a simple mathematical value.
5 minus 5 equals to 0.
It wasn't like it was negative, some irrational negative square root, you know, x is equal to what here? Solve for x, divide the negative 5. I mean, all right, we gotta laugh. It's just a what? Are you kidding me? X value is just negative 1. But do you see what we did? We used calculus. We said slope of straight line equals slope of curve. Then we got a little lost. It was getting a little weird. We were worried. Then we said, man, maybe I can substitute something. All right, Art?
Yes, sir.
And I substituted it, got all the same variables. Now that I know this x value is what? I'm telling you right now, and that's called the crux move, we got this problem solved. We'll get over here. No problem now. I think you're going to see why. We'll get no problem getting this lamp now. If that's -1, though, how do you get the y? Plug it in right there. And when can you figure out what y would be? Notice it's got to be positive. So what's -1 squared plus 4y squared equals 5? Let's plug it in there. That would be 1 plus 4y squared equals 5. And by the way, everyone, thanks for being patient on this problem, but problem solving is important. It's a good skill. And y equals plus or minus 1. Which one is it? Look at the picture.
Plus.
Plus. Everyone, do you agree now? We're going to have no problem getting this? Hello. This is x. And I'm looking for this number right here. And this is on the same straight line as these 2 points. Can't we get it? Slope between these 2 points must be equal to the slope between these two, right? This is going to be no problem to solve now. Right, Art?
Yes, sir.
Oh, no problem. And when the slope between these 2 points, let's find it. It's got to be equal to the slope between these 2 points. The only thing is, when I show my work here, maybe I shouldn't call this y, because I already called what y earlier? That y over there. So maybe we should call it something else, like
Y1.
y Kayla. You know, I mean, just something else. Y sub 1, or right? It's just something different. So you don't think it's that y when you look back at your work. How did I solve that crazy one? Josephine likes this, I can tell. We'll put this as bonus. One of these, right? I'll come up with you. I can always come up with a good bonus like this. All right, everyone. So I get all this worked out. What's this y value now? That's 1. So here I'm going to finish this up. To finish the problem. Everyone, what's this slope here? 1 minus 0 over -1 minus -5 must be equal to, that number must be equal to, anyone want to do the slope with this one and this one, or this one and this one? Doesn't matter, it's on the same straight line, right? Y sub, what do you want to call it?
Y sub 1.
What was this called? This was called a pole? How about y sub p? Y sub p for pole. Y sub p minus 1 must over 3 minus what? We're going to solve this. That's 1 over what? 4? Anybody know what y sub p is?
Yeah.
It's a simple number. Would have been easy to guess. Can you figure out? Look at that ratio. 1/4 must equal y sub p minus 1 over 4. Nope.
Oh, I'm sorry.
You'll get it. You'll get it. And look at the picture, Cal. You'll crack up.
Yeah.
It wasn't even a tricky, goofy looking. This is just a what? I'll flat out what?
2. That means.
Isn't that 2?
Mm-hmm.
Y sub p is 2.
Wait, I lost you. What did you do after that?
After this, we got x equal to -1. Right, Amber? Once we knew that, this problem is getting solved. And you go, why? I knew the point of tangency. And I put it here. But then this wasn't here yet. You go, now how do you get that? Once you knew that was -1, we plugged it into this equation to see what the corresponding y would be. We solved for y here. We got plus or minus 1 because it's up in the air, it's the what? Positive 1. But now you're like, Amber, we're like, the slope between these points must equal the slope between, I call this y sub p, between these points. And you'll get it. The key was, the crux move was trying to figure out this what. Does that make sense? All right, this is problem solving. Like, it's things like that. If I can just get that point, I can get this thing solved. And we knew it involved calculus with derivatives and slope. Slope of a straight line equals slope of a curve. By the way, that's a great problem solving skill. So, Josephine, I have to give a good bonus problem where the key strategy is you're going to say, all right, slope of a straight line must be equal to the derivative of that crazy equation, right? But what makes it crazy, you get down to something like this and everyone gets confused. Take your eyes, look back to see if you can substitute something. You follow me? That's what you do. You go, wait, can I substitute something? This is a system of equations where I can take this equation and this equation. But it was neat. I was watching their faces. Kel and a couple others go, wait, you're getting the same equation as before. It almost looked like it, didn't it? That does throw you off. You think you went in a circle. It makes the student frustrated. It was a tad off. This had an extra what on it? Thanks. You know, a great job with that. And thanks for being patient.
I was trying to do what is it, Pythagoras.
Were you close to this?
No, what I did was I took the whole thing as 8, like -5 unit,
Yeah.
and that unit as 8. Then I was kind of lost. I was doing the derivative. I'm like, okay, I just need to do the mid-value theorem, and I kind of got lost. I was thinking differently.
Would you remind me, before you leave today, I'm gonna give you another one that looks like this, something like this? If you find this stuff fun,
Yeah.
you know what I mean, I'll give you one. Okay, give me another one where it's like you gotta kind of do what? Derivative, slope of straight line, substitute. Cool? All right, hey, in your notes, would you put section 3.6? You know what this is titled?
Logarithmic, right?
Yep.
I have a question. Is this going to be on the test?
Oh, that last one?
Yeah.
Yeah,
So,
sure.
that's a good one, isn't it? Tell you what, I won't put it on there, but maybe I'll give you a good bonus like that.
Okay.
So that gives you like incentive to what? Kind of know what happens, so maybe you could try the what? Bonus. What were the key moves in that problem? Key moves was slope a straight line, or here's a key move, just guess, 1 and 2. Remember the answer was 2? Hey, but slope a straight line equaled derivative of curve, but then we had a mixture of x's and y's. We were frustrated. The second key strategy was substitution. Take something to substitute so you get all the equation in one variable. Then you're rock, then you're rolling. Then you're moving. It's kind of cool, right? Yeah. I'll give you one thing. Remind me, Sarat in the class, give you one kind of practice like that.
Okay.
All right, when this is 3.6, what's this on? Derivatives of?
Logarithmic function.
Logarithms. So I'll just put logarithms and I'm going to just put in parentheses, derivatives, logarithms, derivatives, or the author wrote derivatives of logarithmic functions. So, let me go over here. What was the derivative of EDX?
E to the power x.
Well, we've discussed this before. Everyone, what's the derivative of ln of x? Does anybody remember?
1 over x.
And don't worry if you forgot it,
Oh,
but we've done it like, I don't know, 2 times, but I never mathematically proved it, and I said I would promise you I would prove it. If you know where a derivative comes from, it makes it easy to remember that. No lie. Maybe you hate math proof, but you know where a derivative comes from, it helps you remember. This derivative is 1 over x. Okay? Cool? So, oh wow. So let me start out. Now when you go look at that and brainstorm, how the heck could we do that? I just want to make sure I do it right when I'm jotting some notes on the board. Does anyone have that up there? Now what's the derivative of y to the ln of x?
1 of x.
1 over x, true? I'd like to just take a moment and show you why. Like, why is this the case? Prove it, true? So what we're going to do is you go, well, I don't know how to do this yet. So we're going to do something at the beginning of this problem. How about we e both sides?
Okay.
We can do that balance equation, right? So I'd like you to put e to the y here, and then over here you have to write what? E to the?
ln x.
Now, does anybody in this class recall from pre-calc that e to the ln of x is very neat? It simplifies very nicely.
1.
Don't worry if you didn't know it, so close. E to the ln of blah is blah. So e to the ln of 5 is 5. E to the ln of 2 is 2. E to the ln of car is car. E to the ln of Fred is Fred, so what's e to the ln of x?
E to the
X. So did you know that? I did this because of that. I was like, oh, I could do this to both sides. This just becomes a what?
Just x.
You like it? But I know it's a strategy. You're like, I would have never thought of that, but this is the math proof. But what's still on the left side, though? That got weirder.
E to the y.
But do you agree? I know it's not explicit, but can't we do implicit differentiation? Do you all see this?
Y.
So if I do this implicitly, I'll be able to get a derivative of dy dx, and I'll figure out what the real true derivative of ln of x is. Sound good? So here,
Implicit differentiation. The right side's gonna be easy, everyone. What's the derivative of x? 1. But this side, remember what you gotta do? Derivative of e to the y would be e to the y. The bells are going off because you just differentiated, Amber, something with the y in it. So I have to, right next to it, write a what? dy dx. Now, can you isolate dy dx?
Yeah.
Yep.
Divide A,
Divide.
And we're like, okay, we're done. But this looks kind of weird, doesn't it? That looks kind of weird, doesn't it? But that's our answer. So I was wondering if you can go back with your eyes and look back in all your nice work to see what was e to the y equal to earlier. And we can substitute it. Where was it?
No, no.
Oh, Kelly saw it. She goes, look right here, everyone. Look with your eyes. What can I substitute for e to the y?
X.
And let's put that Helmo symbol, math proof finished. Or QED. We proved it. That's how you find the derivative. That's why the derivative of ln of x is what?
Why'd you
Correct.
switch the y and the x?
You mean here?
Yeah.
Oh, I just went back to see what I could substitute for that. Because Amber, isn't that a goofy looking derivative? But can I substitute that for that? Look, e to the y is equal to that. Isn't that cool?
Yeah.
And that's
Do you have
why.
to? Do you have to?
Well, this was our math proof. That's what I mean. This is the math proof. Amber, that's what we're saying. Like, it's kind of weird. It's like, boy, I wouldn't know to do this. It's a math proof. We're proving why this is the derivative. Wasn't that cool? I know. All right, but now that we got that, can we do something like this? I want e to a u. Can't we say that the derivative is always u prime times e to the u?
Yes.
Isn't that really what goes on? Amber, you were doing it earlier. What's the derivative of e to the 4x? E to the 4x times up?
4 e.
What's e derivative of e to the 5x? Of y equal to e to the 5x?
5 e to the 5x.
That's right. So here's another way. Let's do it now with ln's. What if y equals ln of u? Then the derivative is u prime over u. Do you like that? Because of chain rule. Check it out, watch. This is the derivative of what? ln of x. But what if this is more complicated than an x? Then we'll have to multiply the chain, the derivative of that. Which would just be the what? U prime. That'll be our g. If you don't like u, you can use g. G prime over g. That's chain rule. So can we do a few? All right, watch. I would like that derivative. The cool thing is this derivative does not have an ln in it anymore. I know. That's the cool part. What goes in the denominator?
2x plus 3.
Piece of cake, right, Ellen? But what goes on top?
2.
Come on, you gotta admit it. ln derivatives are easy. Is that it? That's it. Wait, can't you? No, you can't simplify. Or sometimes they're fun. Look at this guy. You can simplify. What if it was just ln of 5x? Watch how you really simplify that dude. I'm serious. You'll get it nice and simple. You'll make it as pretty as that guy over there. I promise you. Watch, Kelly. You'll make this guy almost as pretty as that guy over there. Because what's this say? All right. Derivative. 1 over, put my g here,
5x.
multiply your g prime.
5.
1 over. Oh, so this is the same answer as what? Derivative of, oh, so derivative of x is the same as ln of 5x. You all agree? Kel, that would be a fun math proof. Prove that ln of x is always equal to the derivative of ln of ax, where a is a constant. You could prove it. You would show it. You could show all that math. Is that what I get with that? All right. Let's do a weird one. I still think I can't stump you. Look. 5x squared plus 6x plus 3. I just don't think I can stump you. I just don't think I can. What is the denominator?
5x squared.
plus 6x plus 3.
What is up here?
10x plus 6.
Done. Unless you want to factor out of 2 out of the top, but I wouldn't. These are fun though, everyone, when you do trig functions. So let's do a couple of those. What do you mean, natural log of a trig function? They're fun.
Let's do it.
All right, they're fun. These are boring, aren't they?
Yeah.
So let's do some elements of trig functions. I'll start out. Come on, trust me, it's gonna be fun. Try that guy. Because listen, people are gonna go, oh, I know a good way to write this answer.
So y prime is
So what goes in the denominator?
sine x.
Well, what goes up here? The derivative of that.
So sine.
Okay, I'm done. But watch. Full credit. Full credit, but I was wondering if someone in this class had another way to write that answer because they know trig identity.
Secant.
Who is tangent of x is
Cotangent.
sine over cosine, so I heard it. Cotangent of x. Couldn't I write it like that?
Mm-hmm.
If you wanted to. Right, Josephine? Tangent of x is sine over cosine, so I might as well just, I can write this a little prettier. Hey, you're okay next. Trig function, when you natural log a trig function, they come out what? They come out nice. Let's try another one. You probably know where I'm going with this one. Cosine. Try that one. Amber, you okay? Did you get the last one? I'll put it back up.
No, I missed it.
Oh, I'll put it back up.
Cosine x.
And when I'll put this, go ahead and try this one. Amber, I saw Amber's face. She's like, man, you erased it too fast. So, hey, Amber, what I did was, I put that down here. Whoop. I multiplied that derivative up here. Derivative sine of x is. But then we decided, hey, there's a trig identity. Because
Yeah,
tangent of x is
cotangent,
sine of x,
yeah.
so let's call it cotangent, right?
Yeah.
I didn't want you to freak out, look at the back of the book and go, right, Claire, like, why did they write cotangent of x? I got that. Oh, yeah, it's the same thing.
Yeah.
But try this, it should do something similar. What's the bottom?
Cosine of x.
Now be careful, derivative cosine is not sine of x. It's what?
Negative.
Negative sine of x, right? Good. Anybody got a nice way to write that? I'll let you. So that's right beside it there, Amber. I want to erase it. I promise. It'd be just like. Ln and trig functions are fun, aren't they? Let's do one more though. I'll wait till Amber has all. Let's do another one.
Oh my god.
But on this next problem, I'm encouraging everyone in the class to really try your best. After you get your answer, scan everything, see if you can factor anything, and see if you can simplify it. Okay? Sound good? Here it is. You ready? We got these. Look, we know these. Everyone see these? Try this. Ln secant. I encourage everyone, once you get your answer, to really what? So try hard and see if you can really simplify and factor and stuff. Okay? All right, what's this here?
Secant x.
What's the derivative of secant of x? Secant of x what?
X.
Anybody see anything?
Yeah, you can cancel out.
I love it. That's what I'm talking about. I love when you don't stop, you kind of look at it and you go, well, heck, the secants do what?
Simple out.
Isn't that cool? So when I told you these trig, with natural log of these trig functions, they're kind of fun, aren't they? All right. I thought I saw one in the textbook earlier. It's on my practice sheet. Try this one, everyone. Take your time, dude. Ln of tangent of x plus secant x. Well, what goes in the denominator?
Tangent of x, secant x. So tan x is.
Here comes chain rule. We multiply the derivative of all that. So let's derive tangent of x. Secant squared of x. Excellent. Plus, I'll put a plus. What's the secant of x?
Secant x.
And I guess we're done. Well, let me step away. I just wanted you all to kind of give it the bird's eye view and say, all right, that's it, huh? Well, is there anything you can factor?
You can
And maybe we can cancel something.
factor out a secant from the top.
Amber, that was a good eye. She goes back out a secant of x in the top, right? And if you did that, oh my goodness, what comes out? That becomes secant of x. That's a plus. What's this?
10 x.
Does anything cancel?
Yeah, with the numerator, denominator.
Don't you love natural log and trig functions? Well, these are the identical. Woo! Woo! What's good? Now, I do want to point out something. Remember I was talking about antiderivatives? One of the craziest things is students have to eventually, at one point, calc 2, find that antiderivative.
Isn't it?
And it's not an easy problem. You got to kind of manipulate and stuff. But if you can remember, that means that this is the derivative of this.
Mm-hmm.
That means the antiderivative of this will be what?
Natural.
That's what the answer will be. Everyone follow me? Okay. If that's the derivative of this, then the antiderivative of this is you go backwards. But that's a tough one in Calc 2. So I'll ask students, anyone remember doing this one? They're like, no. All right, everyone, you know we're almost done with 3.6? And we'll talk about 3.7 today because it's fun. Before we do, there's one more goofy type of problem. We have yet to see something like this yet. Look at this guy. This is fun. Come on, we haven't seen this yet. Y equals what?
X to the power x.
X to the x? We've seen x squared, we've seen e to the x, we have not seen what? Exponent x. So it requires a special type of differentiation. You go, what is it, implicit differentiation? Well,
Yeah.
it's more of called logarithmic differentiation. So if you want to put that in your notes, you can. To solve y equals x to the x power, and you want to differentiate it, it requires a specific type. We call it logarithmic differentiation. Wait, that didn't have a log in it. I don't care, it's kind of goofy, right? The base has an x and the exponent has a what? X. So it requires a special type. It's going to be called logarithmic differentiation. So you know what step 1 is? Because it's so goofy? We actually are not going to e both sides like in that math proof. Our first step, we're going to take the natural log of both sides. Only do that for what kind of problem? This kind of problem. X to an x, I'll give you another example. X to the sine of x, if you want me to work that problem. So, first step, do what?
Take natural log both sides.
Because if not, we had nowhere to go. We couldn't go anywhere. So we start out like that. Everyone see that?
Mhm.
Now don't forget we did that. We wrote out on a y on a y. We'll come back in the end of that.
Doesn't y become the exponent or something?
Oh, she's on to something good. Hey, before I finish this up, does anybody remember what ED on a blah was? What's ED? I don't even know. How do you spell blah?
LAT?
B-L-A-H? Is that right?
Uh-huh.
So, or what's ED on a blah then?
Blah.
So what's ED on of x? X. What's ED on of y?
Y.
Y, right? Everyone agree?
Doesn't
All right.
that become x natural log x?
Uh-huh.
Oh, good eye. All right, Steve. So when I took it on both sides for this special case, he goes, you know what? Yeah, you're allowed to move that power in here. It's a property of logs. And you definitely want to do that. So I'm going to bring that dude down now. Now all we have to do is implicit differentiation. Woohoo! Seriously. That's all we're going to do is implicit differentiation. I'm serious. That's all we'll do. But what rule do you need on the right? Please spot it.
Product.
Product rule. You need product rule on the right. But we'll just do implicit differentiation. Differentiate both sides with respect to x. If we differentiate Amber anything with a y in it, right next to it we'll write dy dx. Okay? So I say we start with this side. It's going to be quick. What's the derivative of x? 1 over x. So what's the derivative of this?
1 over y.
1 over y.
dy dx.
And then Josephine, I'm differentiating implicitly because I differentiate something with a y in it. Right next to it I write dy dx.
Now why'd you put the y on the bottom?
Oh, look. You follow? That's exactly right. We just had another variable. That's how chain rule works. That could have been like a G. Remember, this could have been like ln of G. I would have said 1 over G and then d what? dg dx. It just happens to be what letter every time? A y. So you're like, oh, okay. What if it was a q? What would it be? 1 over q times what? dq dx. Or even better, what if it was what if this was ln of t? 1 over t times what?
dt over dx.
There you go. But everyone, I'll go back. What was this? It was a y, so I'll say 1 over y times,
dy dx.
and our goal is to find dy dx, so we're going somewhere. But everyone, you do need product rule there.
So x.
There's m, there's n.
Yeah.
First,
X 1
what's
over
the derivative of the second?
1 over y dy dx.
Yep, ln of x, derivative is 1 over x, Amber, good. You agree? So first, derivative of the second. If you need to, you can label these. But I know we just learned product rule a few days ago, so you can label this. Josephine?
Why the y rule of x isn't a constant?
When x, that right there is a variable, right? If that was a constant, we would not have to do product rule. But we have to do product rule because we have a function x times another function, natural log of x. The key is the variables. We got a variable times a function of the same variable. I know, but if that was just like a 3, Josephine, 3 on a max, we don't need it. Because the constant rule, we can just leave the 3 in front, right? But Josephine, I do want to point out, these come up a lot. Things like this in calculus. X ln of x, you need product rule. X e to the x, you need product rule. X cosine of x, you need product rule. And there, you can just imagine how many times I've graded calc tests, and that's where students made errors. They missed product rule. It's because it's a variable there. So what I'm going to do, m times m prime plus n times m prime.
This is going to be x times 1 over
1 over x, good, plus
ln x
ln x, I'll put parentheses around it,
times 1.
times a 1. Now all you got to do is get dy dx by itself, you're done.
One second, professor.
What's that?
Oh, sorry, that side is x, not y. Sorry, x. No, okay, I got it wrong. Sorry.
Oh, okay.
Hold on a second.
Hey, anything you want to simplify on the right side though? Do you see anything, Josephine, I can simplify that right? Now that I did the product rule? X times a 1 over x will just be a 1. So let me rewrite this. 1 over y, dy dx, equals 1 plus natural log of x. Right? Now the only thing I got to do is isolate dy dx. That's it. That's all I have to do.
Can you substitute 1 over x for 1 over?
Yeah, you can do 1 over y.
Can't do that.
One
There's
over
something
x.
else we want to
Just
do.
multiply.
For this last step here, Kelly, I do want to get this by itself.
Times
So I need this 1 over y off here. So I have to multiply a y on both sides?
Yeah.
Amber, great idea. So I'm going to write that. But I'll be honest with you. When here I go, I'm going to multiply a y, so I have to put a parentheses around this what? Did everyone see this?
Oh, then you have to put the original value of y over there, right?
There you go. So here's what I'm going to tell you. If you check the back of the book, great job on this, you will not see this. Because the author desired, and I think you'd want to too, is write this answer all in terms of x. So look back in your work. Look all the way back up here. Is there something I can put in place of that other letter y? Look all the way, go to the beginning.
X to the x.
Let's do it. Everyone okay if I put that here?
Uh-huh.
So let me write it. X to the x. That's what you'll see in the back of the book. I call back
Are
of
you
book.
going to write it on the test that you want it in terms of x or in terms of y?
Nah, I would accept that. Well, hey, what if I did a multiple choice on the final? I would put it like that. Hey, this is what I encourage you to do. When you don't have to do 1,000 of these, but would you try this guy, the one I think I put it for homework problem? Don't do it now, but would you try it like tonight? What was that? And would you just try it? It would be very what? Very similar. Would anyone try that one? But you do need what? Logarithmic differentiation. Watch, we'll try it now. Isn't that funny? X to an x. If you can remember that, how do you differentiate it? Y equals x to the x. Logarithmic differentiation. Take the log of both sides in the first step. Cool?
Sarah, did you like it? Should I put that on a test or no?
No.
She goes, no, she goes, don't put those. But I can do ln of a trig function, right? All right. ln of secant, ln of secant plus tan, ln of cosine, ln of cosecant.
Yeah.
Well, no, I won't do ln of cosecant, because then you Belraz, we'd have no derivative of cosecant. I know you all know these derivatives, but you don't see that as often.
Who came up with this, Euler or Leibniz?
Oh, good question. I'm going to say Euler. But they both kind of hit, sometimes they hit things hard at the same time.
Gotcha.
Those are some smart guys. This guy's like the smartest in the world ever. For math. I'm going to get another one of these one day. Well, another one of these guys come one day.
What about Tau? Terence
And
Tau?
people, when they just couldn't solve problems back in the day, they go to him. He'd be like, give me a second. He had the answer like 2 days later. You know? Did you ever see the bridge problem? Where you're like, we're trying to figure out a way to cross all these bridges, but we want to go to a bridge once. They went to him, it involved mathematics, and he comes back and he goes, it's impossible. That's his answer. And he had all this graph theory. All this graph theory. So when I teach the lowest level credit course here at it's a credit course at Anne Arundel, it's called Math 100. But in that course, we do Euler circuits. It's fun. We figure out paths, like the quickest path to take, and things like that's fun. They're called Euler, named after him. All right, well, the last thing we're doing today is 3.7. We'll do a couple of these. EVA, what's the derivative of position? Velocity. What's the velocity? Acceleration, right? Someone agree? Rate of change of position with respect to time, we call that velocity. Rate of change of velocity with respect to time, what do we call that? Acceleration. Someone agree? So I'm just going to put PVA up here. Because if this was like a y, then what would this be? Y what? Y prime, what would this guy be? Y double prime. Someone agree? But when the author likes to use the letter S for position. So if I called this position P, I did PVA. If I called it position S of T, what would velocity be?
S of prime.
S prime of T is velocity. What's acceleration?
S double prime.
There you go. Y'all good? Yeah, we won't do jerk. We won't do jerk, which is third derivative. Rate of change of acceleration with respect to time. So when I'm in 3.7, we'll do a couple of these. These are fun. You know, throw a rock, stuff like that. Woohoo! I want to start with number 1 on page 233. I don't often do number 1, but it's a good one. Here's the function. And when ft.
Is this related rates?
What's that? Yeah. Oh, no. Good question. Related rates. I want 2 days for it.
Okay. Yeah.
So today we'll wrap up today. We'll wrap up 3.7. I mean, I'll get your questions tomorrow. But you know what that gives us? That gives us Wednesday and Thursday to really make sure you know this last section called related rates. Is it hard, Doris? No, but every circumstance changes. You know, volume of a what? Cylinder, volume of a cone, volume of a box, area of a box, and all this stuff. And you try to deal with related triangles and how fast things change. But this stuff, you won't find nearly much, you won't find it as challenging. And it's kind of fun. We just need to know that, right? All right, good. They've got t cubed minus 12t squared plus 36t. First question. All right. When did you find the velocity? Oh, and I should mention this. I'm sorry. I won't run the board. F of t does represent the position of a particle. All right? The position of a particle. A particle moves according to the law of motion. S equal to F of t. T is greater than or equal to 0, by the way, everyone. T is greater than or equal to 0. T is measured in seconds and F is in feet. Okay? T is greater than or equal to 0. T is measured in seconds.
S's and feet. What do you all get for velocity?
3t square minus 24t plus 36.
Does this section look tough?
No.
Good, that's what I meant. So Mel Raj, we'll spend 2 days on related rates. Because this, is that hard?
No, not
Good,
really.
but hey, let's keep going. I had a bunch of A, B, C, D, E's here, okay? The next question. Now, if you have to, use your calculator, I don't think you'll need it, but if you have to. Could you sketch the velocity graph? Could you sketch this velocity function you just brought up?
Yes.
And feel free to call this velocity function v of t. Now, does anybody know what the shape of this would look like?
3t square minus.
Boston, it's got a t squared, it's probably what? Like this? But a lot of you may pull out your calculator to graph this, right? You can. But if you're like me, I'm like, I don't feel like going to get my I got chalk on my hands, I'd have to what? Get chalk on my bag, so I'm just thinking I'm gonna find the x-intercepts. So how can I find the x-intercepts of this? I was thinking I could just factor that. Now wait, can I factor this, dude? Let's just see. I can factor out a 3, what would I be left with? T squared minus 8t plus a, how many times 3 on a 36?
12.
Now, can you help me factor this so I can know where the x-intercepts are? Here's time. These x-intercepts on this axis. Two numbers that multiply to 12 add up to -8. -2 and -6? I know where this parabola is sitting here. I didn't even have to get out my calculator. It hits at 2, where else? There it goes. Hey, what was it when it was 0?
36.
Yeah, I just didn't feel like getting on my calculator. So it was up at here, 36. Then it came to 2. Halfway between 2 and 6, it got to its what? Lowest point, you agree? 6, because of symmetry. Do you all agree? Now, if you want, you could remember, wait, what's negative b over 2a? Do you remember that in pre-calc? They always made you do negative b over 2a for a vertex. Don't worry if you forgot that.
Negative
It's a
b-
formula for finding the vertex of a parabola.
Yeah,
Negative, that's b and that's a.
2a.
If you want to put it down, Kelly, negative b over 2a will give you the x value of the vertex. And you'll notice, what's negative 24 over 2 times 3?
6.
4.
4.
So at x equal to 4, t equal to 4, you got your vertex. But I don't think I needed that. I just did this. Obviously, if it hit at 2 here and it hit at 6 here, halfway between it's going to hit its what? Lowest point. Does that sound good? Is everyone okay with this? And by the way, I say we sketch this out to t equal to, you might say infinity. How about for 0 less than or equal to t, and let's go up to like 10. So what would this thing keep doing?
Up to
Keep going up
12.
here, we go. I mean, it gets pretty high at 10.
Mhm.
Remember, this is the velocity of a particle. So do you notice something? Velocity can be positive and velocity can be what?
Negative.
Negative. Now if it was me moving, let's say this is describing me. Velocity is positive when I move to the right. Wait, you're looking at me, so I better go this way, huh? Shame on me. All right, let me go this. Velocity is positive when I move to the right. Stop, I turn around, my velocity is 0. When I move to the left, my velocity goes what? Negative. It's just objects, particles that move like this. Or maybe up and down. Does that make sense? I threw up the chalk, it had negative velocity on the return path. If I went like this, then like this. What if I was like an ant? Positive, negative velocity. Cool? Yeah, all right. So there's the velocity graph. All right. The next thing is, you're going to use this to answer a question. Use this graph. It was made for a reason. Letter C. When is the particle at rest? Use your graph to see this. When is the particle at rest?
So v equals to 0, right?
You know, particle at rest, everyone, that means time, or excuse me, not time, velocity, your velocity is 0. The particle's at rest, the velocity is, you look at the graph, when was velocity 0?
2 and 6.
So this is your velocity graph, this is your velocity function, this is v of t. When was it at rest? When was velocity 0? At 2 seconds, when else? 6 seconds. Anybody agree? It's almost like this. If this was me, let's say this is me, ready? During the first 2 seconds, I ran to the right. 1,000, 2,000, stop. Because my velocity is what?
0.
0. I stop, turn around, I have a look. I'm not moving. My velocity is what? 0. But then I moved in that direction. 3, 4, 5, 6 seconds. I stop. Now I'm moving what? Back this way. Does that make sense? But when was I at rest? When my velocity was 0 at rest. The answer? What do you want to put? T equal to
2 seconds.
2 and what else?
6 seconds.
What is that supposed to be? 0 is less than t, is less than less than?
What's that?
What is that? What? Okay, never mind.
Good thing. Done a great job with this. I have a letter D. When is the move? Oh, you're going to get this because you just saw my movement. When is the particle moving in a positive direction? You can write as an interval. When is the particle
When t is greater,
moving in a positive direction?
when t is greater than 6. Between 6 and 10, right?
All right. You're going to look at this graph, everyone. And whenever you see that graph above the x-axis, that's when it's moving in a positive direction. And remember me moving? I was moving in a positive direction that way. I was moving in a negative direction that way. So remember I was like 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. So when was I moving in a positive direction? From time equals 0 to time equal to 2? Well, when else? You can use open parentheses for your interval. Union, when else?
6 to infinity.
6 to infinity.
Or
Since
10.
I said only about the 10,
So,
I'll put 10. But let's say, like Kayla, let's say you wrote infinity here on your test. So I wasn't wrong. She's got it. She knows if this went on infinitely, that's what it would be. But they did just do some particle from 0 to 10.
I have a question.
Sure.
First of all, on the 10, it should be a square bracket, right? Next to
You mean closed bracket?
close bracket, yeah.
I'm going to keep it open. If you want to, you could.
Okay.
That's a good question.
And second question is, that is a declining slope. So shouldn't that be negative towards that? That slope is so. Is that a positive? Should be like it's.
So this would be a negative slope of v.
Yeah.
Do you agree?
Yeah, that's it.
But it's positive slope of this.
Oh, okay, okay.
Do you remember that? Oh, good, good. He sees it.
Got it.
Doing a great job with that. All right, let it read. I'm going to put a star in this guy. There's so many ways to look at this. When is the particle speeding up? So I desire to give everyone an easy way to solve this. And I'm going to tell you what I recommend. I was just discussing this with my pre-calc students. Who takes physics? Anybody know the definition of speed?
Distance.
I heard it. He's a physics. There we go, Belrise. Magnitude of what?
Of velocity.
That's right. Someone, would you put this down? Speed is magnitude of velocity. Speed is magnitude of velocity. Would you put that down somewhere? If we know this, I think this problem's going to be a piece of cake to solve. There's other ways to look at this. That is. Magnitude meaning like the size of it, and we're going to keep it positive. Speed is always referenced as a positive number. When I was going 55 miles per hour on Route 50 East. Then I was going 55 miles per hour on Route 50 West. I was going in a total opposite direction. I'm not talking about velocity, I'm talking about what word? Speed. You go, but isn't that velocity? It's the magnitude of velocity. Cool. But like you said, Josephine, oh, so it's just the absolute value. So I think the easiest way to answer this question, if speed is the absolute value of velocity, why don't we just graph speed and look to see when it goes up and down? You go, well, I don't know how to do the absolute value of this graph. I'm going to do it right below it, okay? So right below this, there's enough room for me to do this. What would the absolute value of velocity graph look like which references the speed? If you've never done this before in a pre-calc class, trust me, it's real easy. What I need you to do is recopy this entire graph perfectly. But if anything goes underneath the x-axis, I need you to reflect it up here. Okay? That's how you graph an absolute value function of any expression. So watch this. Is this up here above the x-axis?
Mm-hmm.
Then I'm going to do the same thing. La-da-da, la-da-da. There it is, 36 coming down. And what number is this? 2. And what's this number over here? 6. But since it's the absolute value, see this part right here? It's going to get reflected up here like that. So it's going to go like this, look. Woo! Then come back in.
Mm-hmm.
And then past 6, what would this do?
Go up again.
I am telling you, everyone, I find this the easiest way to answer this question. Because now go look at, this is your speed graph. Look here. Look, I'm slowing down. I'm speeding up. I'm slowing down. You follow me? So can you answer the question now? Look carefully at all those numbers. Right? When was it speeding up? From 2 to what? 2 to 4. Anywhere else? Where else did it speed up? 6 to infinity, but we only went out to what?
10.
That's when the particle sped up. Like, you know, speeding up. Now there's other ways to do this. But I'll tell you, I don't recommend them just because of grading the problems over the years. Somehow that gets people. What's an easy way? Look at the what? Look at the speed. Look, up, velocity. Now some people say, oh, if your velocity's negative and your acceleration's negative, and they have all these other tricks to do it.
Where there was a positive.
That's right. You know, let's put letter F, but no one misses this. Can you come up with a formula for acceleration?
Yes, 60 minus 24.
So acceleration is the derivative of what? Velocity, where's velocity?
3t
Somebody
squared.
packed at letter A.
Yeah.
Everyone, what's the derivative of that velocity? 3t squared becomes 6t. And when you can call this A of t, does that sound good? A of t and minus 24? Does that work? No, great job. All right, let's find another good one in here.
How'd you get the formula again?
Oh, over here? You'll find this real easy. So remember how we're talking about position, velocity, and acceleration. And the derivative of position is velocity. Derivative of velocity is acceleration. S prime t, S double prime t. Cool? So, velocity is the derivative of position. And then how can you get acceleration? It's the derivative of what? Well, it's the rate of change of velocity. Oh, just simple derivative. What's the problem? What do people miss? This. And I think it's easy if you just graph the what? The speed function. Look, slow down, speed up, slow down, speed, right? I know. All right, everyone. Let's go to page 234. Let's try number 9. Now, I might not answer every question from 3.7, so when you come in tomorrow before we do related rates, let me make sure I do any problem from this section, or any problem from 3.6, or you still might have an old chain rule problem, right? You might have an old chain rule problem. Here it is. All right, what do you got? This is number 9. And when a rock is thrown vertically upward from the surface of Mars, okay? Its height after 2 seconds is this. And this is the height of this rock. For what planet?
Mars.
Mars, because if this is Earth, we all know gravitational pull. All of you, and you'd be like, Professor Messer, your math formula is incorrect. This is on Mars. All right. H equals 15t minus 1.86 t squared. Letter A and letter B. I think letter A is going to take everyone in this class like a minute to solve. Letter B, not hard, just a couple minutes. We'll be able to wrap up. Letter A. Everyone, what is the velocity of the rock after 2 seconds? What is the velocity of the rock after 2 seconds? Anybody know what I should do?
Yep.
First of all, do I plug 2 in here?
No.
No, that's height.
No, you
Plug
do.
in.
How do I get velocity? I get the what? Derivative. You want to call it v of t? So I'm going to write v of t. And what's v of t equal to? We can call velocity v of t. That's h of t.
Can you do H?
Position, right?
Yeah, can you do H prime T?
He says you can write it as h prime of t. I love it. H prime of t is v of t. True?
Yep.
Good job, Art. And you get 15 minus, what's that derivative?
3.
3 point what? 7 2? Is that right? 7 agree? Cool. Now how do you find the velocity of 2?
Just put a
22.
2.
And what's good notation? V of what number?
2.
Or as you said, Art, h prime of 2. Did you know your calculators have a derivative button where you just say, take the derivative of this at 2. Did you know it could do that? It's math 8. But you'd have to type in this and put letter x, put comma x, and then say comma 2. I'm serious. Math 8 will do that. It doesn't give you the derivative expression or formula, but it'll differentiate at a certain value. Cool? If you want me to show it to you, I'll show you tomorrow at the end of class. Now, and what is v of 2? What's 15 minus
7 point something. 7.34.
7 point what? So what's 15 minus 7.34?
So that's 8.66.
7.56.
7.56. Sorry.
Now let's go back and see what the units were for this problem. They have to tell you. T was in seconds
Meter per second.
and height was in meters.
Is it 7.34 or 7.44?
7.44?
7.
Was this 4.4?
Yeah.
Yeah, 7.44. Yeah.
Josephine, thanks. But this is still what? 7.56. And what's the units? Meters per what? None of this? But yeah, hey, if anyone's curious here, math 8. You tell the calculator, you type this in, and then you go differentiate it, time equal to 2. And it'll give you that number. Let's do it for you. Cool? But that wasn't hard, right? We don't need that button. That's why I rarely use it. Letter B. This is interesting. Listen to this. Hey, last question. What is the velocity of the rock when its height is 25 meters on its way up? So what is the velocity of the rock when its height is 25 meters on its way up? Why do they say on its way up? Because when someone threw the rock, what happened? How many times did it reach a height of 25 meters?
Once.
Once, twice. Does everyone agree?
Mhm.
That's what's happening on Mars. The rock, it hit 25 meters on the way up, then it hit a height of 25 meters on the way down. They're saying, could you find the velocity of the rock when its height is 25 meters on its way what?
Up.
Up. First step. I was wondering if someone can help me out with this. Whoops. What's the first step here? I'm going to set 25 equal to something. But read the problem carefully. It's not too bad. When word problem, would you read it carefully? What am I going to set 25 equal to?
H.
H.
Uh-huh.
You all agree? Excellent. Good word problem solvers right here. You see it. Like, all right, height is 25. So go back to height. But I'm curious. Here we go. I'm looking at you all. I'm thinking, how do you want to solve this? Are you,
You want to solve for t.
yeah, because you want to solve for t? And everyone, we're going to get 2 answers for t. Do you know that? See the quadratic?
We can't get it.
But you won't be able to factor this, so we got to use what formula? Quadratic formula. But if you're like me, everyone, we're now in calculus. This is an application problem. If you like to sit there and do your negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, you want to do it, you can. But I like to solve this with a calculator. That's what I do. How do you do that? What I do is I just graph this to see what the t value is. Cool? But if you want, you could do your what? Quadratic. Let me get this whole thing straightened out here, because I'm just trying to solve this equation, right? What would it be?
1 minus 8t squared.
1.86t squared minus 15t plus 25 equals 0. Is that, everyone agree? Is that a quadratic? Everyone agree I put it all on one side of the equation? Yeah, how do you solve quadratic formula? But everyone, did you know you could pull out your grapher and just graph the thing? I'm gonna do it. I'm upset though I showed this to my pre-calc students how to do this, and then when I put it on the calculator, they know how to do it. It's not hard. I'm just using my grapher. If you want to do quadratic formula, go ahead. You all know it, right? You've done it so many times in pre-calc. What I'm going to do though, Amber, I'm going to go to my y equals and type this equation, all right? I'm going to type it out. And what's the equation? 1.86x squared minus 15x plus 25. Is it okay I'm using x on my calculator? Yeah, so this is what I put in my grapher. Why? I guess I'm lazy. I like to use technology to solve the quadratic formula. Now, you know what else I'm going to do?
Wait, how did the negative get over to the 15?
I added this on both sides, and then I added this on both sides, and I subtracted 15 on both sides of the equation. Cool? And then when I get this, and I'm going to write another equation, y equals 0. And I'm going to tell my calculator, would you find where these intersect? Where these two things intersect will be the what? The answers. So where's the grapher? Hey graph. Where's the intersect? I go to second calc. And when it's second trace, and it's called the calc method. Now which one is intersect on that list? Which one's intersect?
5.
Number 5. I'm going to go to 5. First curve, I just hit enter. Second curve, I just hit enter. Guess I just hit enter. And I just found the time. Or I just found out what this answer is. Not the answer to the whole problem, everyone, but I know the time. I'm going to solve this. Let me just make a note. The solution is when t equals 2.3534952 seconds. I just didn't feel like doing what formula? What formula?
Quadratic.
Quadratic. Now you may do quadratic formula. I just thought I'd use my graphing, right here, my graphing calculator. This $100 tool to my advantage.
How do you do that second?
Oh, I'll do it with you.
Okay.
You still got a minute. It's easy. You put both of those in the y equals. You go to second trace, the calc menu. What button am I looking for? It's titled what?
Intersect.
The intersect. And I go to it, and when I hit it, Art, it asks 3 questions. I just hit enter, enter, enter. It's going to tell me the answer where these two intersect. Do you get 2.35 something, 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 something?
No, the second trace.
Yep.
Then intersect. Then you hit enter, enter.
You hit enter, first curve. You go enter, second curve, enter. Oh, it's not going on. I'm going to hit trace just to see if it gets on there. Sometimes I get trace to get it right on there. Did it work? Didn't work on that one? Yeah, I'm going to hit zoom 6 just to zoom in your calculator. All right, second calc, 5. First curve, enter. Second curve, enter. Oh, I know what we should do. Trace, let's put the cursor near it first. Then you'll be fine. Can you see the cursor there? Put the cursor close. That's good enough. That'll work. It's going to work now. If you put the cursor close to it, I should have said that. Put your cursor close to that in the x-axis and it'll work.
Okay.
Cool? And one more thing, and I'll get your question here, Josephine. I'm getting this for my solution to quadratic formula here, but I used to graph it. What would I do next to solve this whole problem? It says, what is the velocity of the rock at this time? What would be the very last step?
Can you plug in
You plug this in where?
for the
Velocity. That is.
Yep. I plug this into the velocity, and I get, let me see what I get. Ready? 15 minus 3.72 times x. And then when I'm getting about 6.24 meters per second. Cool? Go ahead, Josephine. You sure? All right, cool. Everyone, great job. I'll see you tomorrow.